Hello, welcome to QM Motion's course on understanding electricity and electronic devices. In this video today, we're going to talk about inductors and resistor inductor circuits. Let's start with inductors. First of all, why do we want to study inductors? Well, inductors have several applications. They're used in radio circuits, they're used in switching voltage regulators, and that's going to be the topic of the next video. They're used to reduce conducted EMI or electromagnetic interference. And there are some devices that behave as inductors. So when switching those devices on or off, there's some special considerations that we have to have. And knowing about inductors will make us aware of those effects that we have to consider when switching those devices, okay? So what are inductors? Inductors are two-terminal devices that can store energy in the form of electric current and magnetic field. So they are built as a coiled wire with or without a core. The internal magnetic flux, right? Remember this when we studied electromagnets, this is an electromagnet pretty much, right? There's some differences there that we're going to see in a few minutes, but the construction is very similar. So they produce magnetic flux inside, right? And that magnetic flux is proportional to the current and the inductance. This would be the equation, but this equation is not really very useful for us because in an inductor, we do not normally have access to this magnetic flux. It is contained within the device, or at least that's the intention. Okay, so what does an inductor look like? This is what they look like. So as you can see, there are different variants of the coiled wire, right? So we have like a cylindrical core here and a very thin wire around it. This thing is called a toroidal core, right? The donut-shaped core, and the wire is coiled around it. Okay, so this helps contain the magnetic flux inside. This one is pretty much the same as this one, only this one is coated and enclosed, right? So you cannot see the wire, but the wire is inside. So the internal construction is going to be very similar to this one. And lastly, this one does not have a core, right? So it's what we call an air core. This one is enclosed in some kind of resin here that helps the coil maintain its shape without affecting what's going on inside. And the symbol can be one of these two, right? So this is a classic symbol that resembles the coiled wire. And this is a more stylized symbol here. So you're going to see both of these. Inductors are considered the dual of capacitors. If you recall from our class on capacitors, capacitors store energy in the form of voltage and electric field. Inductors, on the other side, store energy in the form of current and magnetic field. When you put a constant current into a capacitor, that produces a rising voltage, and when you apply a constant voltage to an inductor, that produces a rising current, okay? So they are dual one from each other. And many of the behaviors are gonna be similar, as we're gonna see in the next few slides. Clarifying what we just saw, right? The voltage across an inductor is related to the rate of change of current through this equation, right? So the voltage is the inductance. The inductance is the main parameter of an inductor times the rate di to dt. Di to dt is differential current over differential time. So this is how fast the current is changing per second, okay? So if we apply a set voltage and we're going to obtain some rate of change of current. If we increase the inductance, this term has to decrease to maintain the voltage the same, right? So the higher the inductance, the slower the current's going to change through it. So if we apply a 1 volt voltage to an inductor of 1 Henry, the current will rise at 1 ampere per second. Same way when we studied capacitors, 1 farad was a very high value of capacitance. 1 Henry is a very high value of inductance. So it is a lot more common to see the inductance measured in millihenries, microhenries, or nanohenries. Okay. So as we just saw, inductors oppose changes in current, and the current through an inductor will change slowly when the external voltage changes. What I mean by this is we just saw if the external voltage is constant, the inductor current will change until it reaches a final value. When the voltage, when the current reaches that final value and we change the voltage to a new value, the current's going to change to adapt to the new voltage, but it's going to change slowly, right? And after long enough time with no changes in voltage, the inductor will behave as a short circuit or as a wire. Let's talk about a circuit with inductors and resistors. Let's consider this circuit here. We have a 1 amp current source, 100 microhenry inductor, and a 10 ohm resistor here. When the switch is to the left, we're gonna have 1 amp flowing through this branch of the circuit, right? Because the current source forces 1 amp through this loop here. So that 1 amp is flowing through the 100 microhenry coil or inductor. When we switch this to the right, okay, we will still have 1 amp flowing through the inductor because inductors will oppose to changes in current, as we saw, okay? So for a while, we will still have 1 amp flowing here. And the current's gonna decay to 0 amps after a while, after a time constant that is gonna be defined by the inductance and the resistance here. So the current through the inductor is gonna decrease slowly. And by slowly, I mean just not instantaneously, because the decay is gonna be pretty fast, right? This scale, as you can see, is measured in microseconds. So in this circuit from after 10 microseconds, which is our time constant, the current's going to be decaying from 1 amp to about a bit less than 4 amps. And after 30 microseconds, it's going to be very low, okay? Now, the time constant is calculated as L over R, okay? And that this has units of seconds. If you recall, when we studied capacitors, the time constant was the capacitance times the resistance. So a higher resistor or higher resistance meant a longer time constant. With inductors, the opposite happens. The higher the resistor, the shorter the time constant. Okay, so that's the main difference between the time constant in inductors and the time constant in capacitor circuits. So after 1 time constant, the current drops to 37% of the initial value. And after 5 time constants, it will drop to 1%, and we will consider that it discharged completely and it reached its final value already, okay? Now the previous circuit was done with the current source, but we are more used to deal with voltage sources, okay? And they are a lot more common in circuits. So let's see how the inductor behaves in a circuit with a voltage source. So when the circuit is moved to the left, there's going to be some current flowing here, okay? And the current through the inductor will raise with a time constant of 1 microsecond to a final value of 50 milliamps, okay? So first of all, where's the 1 microsecond coming from? So 1 microsecond is 100 microhenries divided by 100 ohms. If you make that calculation, you will end up with 1 microsecond. So that is your time constant. How do I know that the final value is going to be 50 milliamps? Well, we said that the inductor will behave given long enough time as a short circuit, right? Or as a wire. So if we consider this a wire and we apply Ohm's law to this loop here, we will find out that 5 volts divided by 100 ohms, that's going to be 50 milliamps. So after long enough time, we're going to have 50 milliamps flowing through this loop. And what is long enough time? Well, long enough time is going to be 5 times the time constant, which is 1 microsecond. So after 5 microseconds, we're going to have 50 milliamps flowing through this loop, right? And the current is going to flow like this. After 1 microsecond, we will have 67% of the final value there. And after 5 microseconds, which is 5 times constants, we're going to have 50 milliamps, okay? Very good. So what happens when we flip the switch to the other side? So when we flip the switch to the other side, these 50 milliamps, we will, at least initially, will still be flowing through this 100 microhenry inductor. Okay? And now the current's going to decrease from 50 milliamps to 0, right? Because we have no voltage or current sources in this loop here. So in the end, this is going to be behaving as a wire, and all the current's going to be disappearing from this loop, okay? Now the time constant is going to be 0.5 microseconds because the resistance is higher, right? So before, with when charging, when the current was increasing through the inductor, we had a 100 ohm resistor here, and that would result in a 1 microsecond time constant. When we flip the switch to the right, the resistance involved is 200 ohms, and the time constant is 100 microhenries divided by 200 ohms. And that's going to result in 0.5 microseconds. Okay. But now there's something very interesting happening here. The current is flowing in this direction here, right? Which is the current through the coil does not reverse direction initially, right? So if it was flowing from top to bottom before flipping the switch, when we flip the switch, it's going to keep flowing from top to bottom. But the current on the resistance is flowing from bottom to top, and that means that the voltage here is going to be negative, right? And the voltage here is going to be positive. So, and if we do the math, 50 milliamps times 200 ohms, that is negative 10 volts, okay? So the voltage in point A is going to go negative to minus 10 volts. And it's going to follow this, this graph here. So the voltage on point A drops to negative 10 volts, and it's going to slowly, and again, slowly is a relative term because this scale is in microseconds, return to 0 volts here. Again, the time constant is going to be half a microsecond. So after half a microsecond, we're going to be 67% through. And after 5 time constants, which in our case is 2.5 microseconds, we're going to be already at 0 volts. Okay. So keep this in mind. We can use a switch and an inductor to generate a negative voltage in a circuit, right? In all the cases we saw before, the voltage in any point of the circuit will be somewhere in between the negative and the positive value of the source. But when we start involving inductors, because inductors behave as current sources, we can have voltages outside our voltage source. And this is the same we saw in the class about current sources, okay? So let's consider another circuit here. Again, we have, this is very similar to the previous circuit, only we swapped positions of the inductor and the resistor, okay? So when the switch is at the bottom here, we will end up having, again, 50 milliamps, which is 5 volts divided by 100 ohms. When the switch is moved to the top, okay, the voltage, sorry, these 50 milliamps will keep flowing through the inductor, but this time through the 200 ohm resistor. So when we do 50 milliamps times 200 ohms, that's going to produce 10 volts here. And because current is flowing in this direction, it's going to be positive on top and negative on bottom, okay? So the voltage is going to jump to 10 volts here, and then it's going to slowly decay to 5 volts, right? Because after a while, after 5 times constant, this inductor is going to behave as a wire, okay? So with the wire, you will end up having the voltage from this source here, which is the 5 volts. But for a while, this voltage here shot up to 10 volts, okay? So let's see what some applications could be for this, right? In the previous slides, we managed to generate voltages outside the voltage of our supply. So this principle can be used in what we call switching regulators, which is going to be the topic of the next video. For instance, to generate 3.3 volts from a single 1.5 volt battery. So we have a 1.5 volt battery and we need 3.3 volts for our circuit, which is a fairly common voltage to power some digital circuits. And we can generate that using the techniques of generating a higher voltage with an inductor. Or some circuits require a negative supply, right? So from a positive supply of 1.5 volts, we can generate negative 5 that we may need in some circuits there. And getting a bit ahead, and this topic will be covered in more detail in the next video about switching power supplies. This circuit that we see here is the basic operating principle of a boost converter. A boost converter allows us to generate a higher voltage at the output. The output would be this point here compared to the input voltage here. So this would be the example of having a 1.5 volt battery here and generating 3.3 volts here. So how does this work? Well, this switch closes, right? And we have current flowing through this inductor in this loop. And when this switch opens, the current keeps flowing through this inductor, through the diode, and will charge the capacitor here, okay? And if we repeat this opening and closing several times per second, we again make current flow through the inductor. So we recharge, if you will, the inductor with current, and then when we open, we discharge the current from the inductor over the capacitor and the load. And depending on how long we keep these closed and how long we keep these open, we can control the voltage over here. And but the voltage is always going to be higher than what we have initially. And we're going to see this circuit working in more detail in the next video, like I said. Now, if you want to purchase or specify an inductor, there are several parameters that you have to look at. The first one is the inductance, right? So if you are going to put an inductor in a circuit, you have to know or have an idea of how much inductance you want in there, right? The next one is going to be the maximum current that it can handle. So remember, it ends up being a wire, and if you make a very high current pass through that wire, you will damage the wire, or at least you will make that current produce some heat and damage the insulation in the wire. Okay, so exceeding that maximum current may damage the inductor. But there's some other parameter, which is the saturation current. Saturation current is the maximum current that the inductor can handle while maintaining the specified inductance here, right? So you have to be careful not to exceed this current. The other thing that you have to keep in mind is the resistance, because the inductor is made of a coil of wire. That wire is not perfect and has some resistance there. And that's usually something, an undesirable condition. So you have to ensure that it is as low as possible, or if it is not as low as possible, you may have to consider the effects of this resistance in your circuit. And the last one is related to the frequency. Depending on the core may be good up to a certain frequency. Remember when we were having the boost converter circuit, we said we would open and close that switch many times per second, right? So there's a frequency associated with that. And some cores are good up to a certain frequency, and some cores behave well at a higher frequency. So you have to ensure that the coil will be working properly at the frequency you want it to work. So to summarize what we saw today, inductors are devices, two-terminal devices that oppose changes in their current, so they behave momentarily as current sources. So if you have a current flowing through an inductor, that's not going to change instantaneously, but it's going to keep that current flowing for a while, depending on the circuit. They are usually measured in microhenries, millihenries, or nanohenries, right? Because 1 Henry is a very high unit of inductance. And the time constant decreases with resistance, and this is opposed to what we had in capacitors. And they allow to generate voltages outside the input voltage, and they are used in switching power supplies, which, like I said, is going to be the topic of our next video. All right, so I hope you learned about inductors, and we'll see you next time. Thank you. Bye-bye.